Okay, today we are talking about the kinetic molecular theory of matter. Let's actually label this one states of matter. I wish that someone, who's going to be a good lab assistant today? I wish that Aaron would go into the lab and there's a balloon, there's a nice little like coral colored balloon in the top drawer. I want a beaker, a balloon, and some, I think there's like a little acrylic plastic block, just some solid. The balloon, a beaker with a little bit of water in it, and a little solid block, okay? And Kesson can go help you if you need. She probably knows where they are, I guess. Okay, the first thing we're going to talk about while those kids are going to get that is, do you know what is meant by states of matter? You've heard of this before, I assume.
Yes.
What are the states of matter? Let's list some of them. We're not going to be able to list all of them because there are several that are kind of more quantum mechanical than they are physical. Solid. Okay. Liquid. Gas.
Oxygen.
Yes.
Plasma.
There are others. There's something called superfluid. There's something called Bose-Einstein condensate. We're not terribly worried about those. These are the ones we need to know. Have you heard of these top three at least? Probably in elementary school, I would guess. Give me an example. We're going to be very basic with this. I just want an example of a solid so we're all on the same page. Rock. I like rock best. Liquid?
Soda.
Let's use water. I think it'll be easier in the long run. Gas?
Gasoline.
No.
Carbon monoxide.
Carbon monoxide. That's a good example. Carbon monoxide. An example of plasma, can you think of one? The sun.
Yeah, the sun.
Not all of it, but the sun is a good example. We'll think of the sun. Nice. Give Carson Gibbons a high five, please. Okay, so we have some solids and we have some examples. I'm sorry, we have some states of matter and we have some examples of those states of matter. What determines, this is what we're going to mainly talk about today, what determines whether something is this or this or this or this, generally?
The real answer.
The real answer. What determines? Yeah, more or less. Let's say this. The more energy, I'm going to put energy because it's not only just about the thermal energy. The more energy particles have in a given substance, the further down this list it is. That's not really a super hot way to phrase that, but what I mean by that is that for many substances, this is not true of everything because some things decompose, so let me use an example that probably wouldn't decompose. Okay, this is a failed 3D print, which is a kind of plastic called polylactic acid, and it's a solid right now.
Wait, can you move that way?
Oops, it's a solid right now. Just put them there, thank you. That's exactly the block I was thinking about. Let's put them over here. Thank you. This is a solid. If we give it a little bit of energy, what's one way we could give it some energy? No. Heat, yeah, I'm talking about heat. If we were to put this over a Bunsen burner, for instance, this would probably burn a little, but it would eventually melt. Melt becoming a... Yeah, so the process of solid becoming a liquid is called, I'm going to put a vocab word in here. What is this? Solid becoming a liquid. Solid becoming a liquid. Melting. If we kept heating that liquid up, it would eventually, let's not use the word evaporate, let's say vaporize, which kind of encapsulates both evaporation and boiling, but we call this vaporization. And then to become a plasma, and we're not very familiar with plasma here on Earth's surface. It is all around us. It's actually the most common state of matter in the universe. Write that down. I know that's on the test. Plasma is the most common state of matter in the universe. Why do I specify in the, well, first of all, the universe is about the least specific thing you can get to, but why would I say in the universe? What am I referring to here? Plasma is the most common state of matter in the universe. Fight? Stars. Yeah, suns, stars. By orders of magnitude, 99.9999999 repeating probably, pretty close, percent of the mass in the universe that we can observe, at least, is stars, and those are made of plasma. And so plasma is the most common state of matter in the universe. When a gas gets a lot of energy, we use this word, it ionizes. Ionizes into a plasma. And we're going to talk about what's kind of going on at the molecular level here in a minute, but for now just know that word, that it ionizes. And that was a vocab word, was it not? Maybe not. It's not, but that's what it is. So maybe write that down because I don't even think that's actually in the text. So you might write that down for sure. It ionizes. Now going the other direction, so what am I going to have to do to go from plasma, for instance, to gas? What will have to happen? A loss of energy, exactly. I'm going to do those in red. If it loses energy, we call this, a plasma becomes a gas, and we call that deionization. Deionization. I kind of use a different noun form for these, so I'm going to change this one from ionizes to ionization. No. Thank you, though. But what is it called? To go from a gas to a liquid? You should know this from the water cycle.
Condensing?
Yep, condensation. Condensation. The question was, oh, I kind of ran out of room, but that's condensation. I think that was a vocab word. So if you can't read that, I apologize, but it is in your book. And then from a liquid to a solid, we call? No.
A liquid to a solid is called
Freezing. Freezing. So we have all the, well, we don't have all the words because there's a secret one. Nah, that's a stupid thing to say. There's not a secret one. But for a solid sometimes can go right to a gas without becoming a liquid first, and we call that sublimation. S-U-B-L-I-M-A-T-I-O-N, sublimation. A solid becoming directly into a gas. Dry ice does this. That's why it's called dry ice. When you get dry ice from the grocery store to keep your ice cream, you probably do this all the time because y'all live in the country. You go to Walmart, you get some ice cream, and your mommy doesn't want the ice cream to melt, and so she gets some dry ice in the bag. And the reason you get dry ice instead of normal ice is because the normal ice would melt into a liquid. And it would make your sack wet, and you don't want a wet sack. And so the dry ice sublimates. Instead of melting, instead of becoming a liquid, dry ice, which is carbon dioxide, sublimates. It becomes a gas with no liquid in between.
One time,
I actually touched example of that would be
Taylor was talking first, Fate. Hold on a second. Taylor should have raised his hand, which you did, but let Taylor talk first. You should have raised your hand.
I'm at it, and she said, don't touch it.
Yeah.
So then I did touch it.
Great.
And it didn't.
Yeah. Yeah, because it's very cold. It's quite a bit colder. Fate.
So wouldn't another example of sublimation be like, cremation?
No.
The body turns to ashes.
Yeah, but ashes are solid. So what cremation is the body, all the things that cannot be decomposed or boiled away in the process of burning, instead just stay as ash, which really usually is a mixture of some of these metals in the body, sodium and potassium. Oh yeah.
Is that why blood tastes like mine?
Sure. Yes, the answer is actually yes to that. So, and then the reverse of this, for a gas to become a liquid, or sorry, a gas to become a solid, I've kind of got a messy little diagram here, but this is called deposition. The only example of this that I think is even remotely good is that if you, there's a process where you can use deposition to plate something with metal. So like, you could generate gold vapor, like get the gold really, really hot. Not only melt the gold, but boil the gold. So there's gold vapor in a little chamber, and you put another object in there, and because that other object is cool, the gold is deposited onto it. So it has gone right from a gas to a solid. That might not be a super good example. I'm sure there are better ones, but that's the only one I could think of. But it's the opposite of sublimation. This This lesson usually has to be at least 2 videos, but we'll get as far as we can. We're going on about 12 more minutes, so we'll probably knock it off and try again tomorrow, but let's finish this up first. There are different temperatures at which these things happen. For instance, the temperature at which a liquid predominantly becomes a gas is called what? You already know this phrase. I said a liquid becomes a gas. We call that the temperature at which that happens is called the boiling point. The boiling point. So let's, I'm trying to think of what color to use. So the temperature at which a liquid becomes a gas, the temp at which that happens is called the boiling point. What about the temperature at which a solid becomes a liquid?
Melting point.
Yeah, the melting point. And here's one of the main things we have to know about this, is that the reverse is true too. The same temperature where a liquid becomes a gas is also the temperature where a gas becomes a liquid.
Wait, so a solid to a liquid is a melting point?
Yep, yep. And then the same exact temperature where a solid turns into a liquid, the melting point, is also the freezing point. What's the freezing point of water? 32 degrees Fahrenheit, 0 degrees Celsius. We actually have to know those. Let's write those down. Freezing and melting point of water is 32 degrees Fahrenheit, which I don't like, and it's also 0 degrees Celsius, which I like a little bit more. And then the boiling / condensation. Why are these both slash? Like why are both of them a freezing and a melting point, and a boiling and a condensation point?
Because both can happen.
Yeah. At that temperature, it's a dual threat. It's going back and forth. That's why I don't know what the temperature is outside right now, but if it gets to 32 degrees Fahrenheit, all this solid water on the ground, which we call snow, begins to melt. It doesn't all instantly melt at once. It begins to melt though. Similarly, if it's already melted, if there's some liquid water there and it gets to 32 degrees Fahrenheit, that water begins to freeze. So at that temperature, both things are happening. Same thing with boiling. When you boiled your water in your little balloon lab, both things were happening. The liquid water was becoming a vapor, and the vapor water that was on the balloon was condensing and becoming a liquid again. And this point, or this temperature is, does anyone know?
What? 212 degrees?
212 degrees Fahrenheit, or 100 degrees Celsius. You have to have these memorized. These are just for water. This is not true of everything, but these are just for water. These numbers need to be memorized in both units, both in Fahrenheit and Celsius. Okay, so I promised what we would do was we would look at what is going on the molecular level, okay? But first, let's kind of define what physical characteristics allow us to say which of these things it is. What is a solid like?
Solid.
It's solid.
The particles are in the same volume and shape.
Good, good. So I'm going to make sure that we can all see this, but I'm going to start over here. Solid. We're going to have 3 boxes here. In a solid, I'm going to draw a little picture of a square for each one of them. It's going to be a little picture, and then we're going to have an example that I'm going to show on the camera too. In a solid, let's say that it has a definite shape and a definite volume. What's volume? Remind yourself from the beginning of the year. What's volume? Yeah.
How much space an object takes?
Yep, how much space it takes up. Here's my nice little solid. What shape is this? Well, rectangular prism. I was going to say be more specific, but I mean be less specific. And also that's wrong. It's not a cube, it's a rectangular prism. What shape is this? What shape is it now? It has a definite shape. It's a rectangular prism. What is its volume? Well, we could fairly easily calculate this, but I don't have my meter stick anymore. But let's say 3 centimeters by 1 centimeter by 3 centimeters. What's its volume? Well, volume equals length times width times height. Volume equals 3 centimeters by 1 centimeter by 3 centimeters. Volume equals,
3 centimeters.
no,
9 centimeters.
9 cubic centimeters. Okay, now look at this. Wait. It's like a magic trick. It's a science magic trick. Now what volume does it have? It's still 9 cubic centimeters. So what the definition of a solid is it has a definite shape and a definite volume. What do you need, Gunnar? Well, I'm not. We're trying to do something here, so you can try that later. What is the solid made out of? What is everything made out of? Matter, material, atoms. Let's do that. It's all made of atoms. So little dots in here. The atoms in the solid should be relatively tightly packed. And what is the motion that they're doing? We have tightly packed molecules or atoms, and they are, what is their action? Vibrating. They're saying just like when you get nervous and you're giving a speech in Mrs. McClendon's class, and you're like, I believe that abortion is bad, and you do this, and you just stand here and you rock back and forth. Are you going anywhere? No. Are you moving?
Yes.
Yeah, you're moving. You're just oscillating back and forth. You're not moving. You're not going from place to place. You're just back and forth. And that's what the particles are doing in a solid. So the particles, we could say, are vibrating. They're tightly packed, and they're vibrating. Yeah, if we're going to tap, let's try to tap quieter. So the particles are tightly packed, and they're vibrating. Does that make sense for solid?
Yes.
What's the next one? Liquid. So we're going to do this for all of them. We have, does liquid have a definite shape? Well, let's look at this.
No, because you can move
Yeah, check this out. What is the shape of this liquid?
the shape of the container.
Well, tell me the shape. You know what shape this is. It's a cylinder. Now what shape is it? It's okay. Now what shape is it?
Asymmetric.
It's a puddle.
That's what
Does it have a definite, is it, wait, hold on, shh. Is it still a liquid?
Yes.
Does it have the same shape? So what should we write here?
definite volume, but not
No, shh, listen, no definite shape, but it does have, how much water was in here before? I should have asked this before I dumped it out. How much water was in here? Kesson, do you remember? There were 300 milliliters. How much is in here now? I'm kind of shaking it, but how much is in here now? 100 milliliters. How much is probably on the floor, given our very simple math? Probably about 200 milliliters. So does it still have the same volume? Does that water that we were talking about still have the same volume? Yes. So it does have a definite volume.
Should we also write takes the shape of the container?
Yeah, it does do that, because that's why. What was it contained in before? A cylinder, so it had the shape of a cylinder. What was it contained in now? Floor, and so it has the shape of floor. So, and then these things, what are the particles doing in the liquid? The verb for solid was they were vibrating. What are they doing in this? Yeah, they're flowing. They're sliding past each other. Flowing, sliding. They're sliding into each other's DMs. That was a stupid thing to say. Let's go on from that.
You have Instagram?
I have an Instagram, yep. You don't know how. Okay, now let's do this one. What's the last one we're going to do for this? Can you guess? Gas. We are going to put a plasma on the bottom, but let's check this out. What's out here? This is nothing, right? What's in frick, there's nothing. Hold on a second. What's in here? No. What's in here? Okay, a little bit of coffee. That's not what I'm talking about. Air. There's a gas in here. There's a gas in here. No, I'm not.
Chug all your hot
Yeah.
coffee like that.
That's okay. But yeah, there's air in here. What's in here then? What's in the room? Air. What's in here now? No, I'm not drowning. Joel, come on. There's air in here now. There's air in there.
Air with a little more carbon dioxide.
Yeah, maybe. What shape is this?
A balloon.
We'll say it's sphere. I mean, it's an oblate spheroid, but yeah, we'll say that's a sphere. Does this, and what volume does this have? Guess.
150.
Guess. You know what a gallon looks like, right? So how much about is this? Maybe half a gallon. Maybe half to 3/4 of a gallon. Maybe 3/4. Okay. What's in here? Air. And what shape is it? Sphere. And how much is it? Half a gallon, we'll say. And now what shape is it? Where did that air go? It's in the room. What's the shape of it now? I mean, it will take a while, but if we came back in an hour, what's the shape of those exact same air molecules that were in there? The room. It's the shape of the room now. It didn't just stay as a little sphere right here. And what's its volume now? The volume of the room. So let's say it for gas then. No definite shape. And instead of saying no definite volume, which is true, you can write that, I'm going to put expands to fill its container. So its volume gets bigger or smaller depending on its container. Has no definite volume. What are the particles doing? They're much more spread apart, and what are they doing in a gas? Bouncing around. Bounce, bounce, bounce around. Bouncing around. They crazy. They're bouncing around. Okay, and then lastly, we have here a plasma. And a plasma has, then you can see there's more energy, right? There's more energy Even just if you think about yourself as one of these atoms, it takes more energy to kind of walk around, which is the example here, than it does to just bounce back and forth. And it takes more energy to sprint around than it does to walk around. Okay, it takes the atoms have increasing amounts of energy as we go down this list. But what happens is, and imagine this, what happens? I don't know how to phrase this without getting gross. Okay, so in this one you were just not bouncing, you were just doing this. In this one you're like walking, and this one you're like running. What happens if you get enough energy and you run at 6,000 miles an hour? What if you're going at Mach 10 like the airplane was in Top Gun Maverick that we watched? What, you, a human being, it's just you. What if you went Mach 10? What would happen to you? Yeah, you'd burn up. Your arms would fly off. Your eyeballs would shoot out the back of your head. I mean, you'd be wrecked. And that's what happens with the plasma. When it gets enough energy, the atoms dissociate. The atoms break apart. The electrons, which, you remember electrons, neutrons, and protons from 7th grade probably, right? The electrons break off from the nucleus. So now, instead of being atoms that are more or less whole, now the atoms are split apart, which we call ions, which is why we call this process ionization. Now let's think, last thing before we have to go, because we're having a great time, what happens as a solid turns into a liquid? The little particles go from, solid to liquid, it melts. The particles go from vibrating to sliding, so there's a little bit more energy. Melting. What happens when a liquid becomes a gas? They vaporize. They go from sliding to bouncing. And what happens as a gas? It's a little bit more energy. They ionize and they become a plasma. The exact reverse, they deionize to become a gas when they lose energy. Those condense to form a liquid when they lose energy, and that freezes to form a solid when they lose energy. Questions?